SpaceX must push Starship launch toward $500 per kilogram, or 400 to 100 tons for a 40-megawatt cluster remain uneconomic. Research models clusters near 5 billion and a 50 billion deployment market. NVIDIA anchors orbital compute, with H100 and Blackwell GPUs in racks scaling toward 20,000 chips in a 40-megawatt cluster. Research models NVIDIA revenue $500 billion by 2030, with 50 to 75 billion incremental. Lunar data centers face harsher radiation, abrasive dust, and 14-day nights that force enormous batteries or nuclear power. Light needs about 1.3 seconds each way, making interactive AI sluggish and favoring backup storage, as Lone Star's failed March 2025 compute mission underlines. Research flags cooling masses up to 800 tons, communications limits, debris risk, and 10 to 20% cost inflation as frictions. Yet base cases send 20 to 30% of capacity off Earth by 2030. StarCloud reports reaching one separation with what it calls the first data center launch in space, shifting debate from whether chips survive orbit to whether space makes economic sense for cloud computing, from clusters in low Earth orbit to ambitious lunar concepts. StarCloud 1 flew NVIDIA H100 processors in November 2024, claiming 100 times orbital compute. StarCloud 2 in 2026 targets H100 and Blackwell, 100 times more power, toward an 88,000 satellite, 5-gigawatt hypercluster built on solar power. StarCloud's proof point is a NVIDIA Hopper GPU running inference in orbit, claimed 100 times more powerful than any predecessor. Scaling means a 40-megawatt system, about 20,000 GPUs, and a 350 by 450 meter solar array, 400 tons, before tackling heat. In vacuum, cooling relies on infrared radiation. A 40-megawatt orbital center needs 120,000 square meters of radiators weighing 400 to 800 tons, enduring swings from 120 to minus 170 degrees Celsius, plus bandwidth limits, replacement satellites, debris, and huge launch costs.